Welcome to the Nocturnal Astronomer. This channel is a quiet place set aside for curious minds who want to drift off to sleep, settle into a study session, find their focus, or simply unwind at the end of a long day. Each episode is a slow, unhurried journey through some of the most fascinating ideas the universe has to offer. My name is Atlas Reed, and I will be your guide on these nightly journeys. I have spent years reading, studying, and thinking deeply about the science of the universe, and I genuinely believe that astronomy, when spoken slowly and with care, is one of the most soothing things a human mind can encounter. The universe is enormous. Our worries, for a moment, become small. And that smallness, strangely, feels like relief. Tonight, we are going to talk about one of the greatest mysteries in all of modern science. Something that cannot be seen. Something that cannot be touched. Something that emits no light, and yet somehow makes up most of the matter in the entire universe. Scientists call it dark matter. And over the course of this evening, we are going to take it apart piece by piece, using only the simplest ideas and the most familiar comparisons we can find. We will begin with the basics. What is matter in the first place? Why did scientists start to suspect that something invisible was holding the universe together? How did they look for it? What have they found, and what do they still not know? By the end of our time together, you will have a clear and genuinely grounded picture of one of the deepest puzzles in all of physics. Let's dive in. Part 1. What is matter? Before we can understand dark matter, we need to spend a little time with the word matter itself. It sounds simple enough. Matter is stuff. It is the physical material that makes up the world around you. The chair you are sitting in. The air you are breathing. The bones inside your body. All of it is matter. And matter, at its most fundamental level, is made of atoms. Atoms are almost impossibly small. If you were to line up 100 million atoms side by side, the whole row would only be about 1 centimeter long. That is roughly the width of your fingernail. Inside each atom, there is a tiny core called the nucleus, and around that nucleus, even tinier particles called electrons swirl in a kind of cloudy arrangement. Now, what makes atoms interesting for our purposes is that they interact with light. When light, which is a form of energy, encounters an atom, something happens. The atom might absorb the light. It might reflect it. It might emit its own light in response. This interaction is the reason we can see anything at all. Everything you have ever looked at in your entire life, every color, every shadow, every glittering star in the night sky, is visible to you because atoms were bouncing light around. This is a crucial point. Ordinary matter, the kind made of atoms, talks to light. It engages with the electromagnetic spectrum. Scientists can detect it, measure it, and study it because of this relationship between matter and light. Think of it like a conversation happening all around you at all times. Every object in the room is constantly speaking to you in the language of light, and your eyes are doing the work of listening and translating. The sun speaks. The moon whispers. Candles murmur. All of it is ordinary matter. All of it is participating in this endless, ancient conversation. Dark matter does not participate in that conversation. That is where things start to get strange. And that strangeness is exactly where our journey begins. Part 2. The universe is heavier than it looks. Imagine you are standing in a kitchen and you can smell something baking. You cannot see the oven from where you stand. But based on the strength and character of the smell, you make a pretty confident guess that a large cake, not a small cookie, is in there. You have used indirect evidence to conclude something about a thing you cannot directly observe. This is, in essence, how astronomers first began to suspect that the universe contained far more matter than they could actually see. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Zwicky was studying a cluster of galaxies, meaning a group of galaxies that are gravitationally bound together and orbiting one another. He noticed something puzzling. These galaxies were moving far too fast. Based on the amount of visible matter he could count, stars and gas and dust, the gravitational pull holding the cluster together should not have been strong enough to keep those galaxies from flying apart. The cluster should have dissolved. But it had not dissolved. It was perfectly intact. Zwicky concluded that there must be additional matter present that he could not see. Matter that was contributing its gravitational pull without contributing any visible light. He called it dark matter. His colleagues were largely unconvinced at the time, and his idea sat quietly on the shelf for several decades. Then, in the 1970s, an American astronomer named Vera Rubin picked up the thread. She was studying how galaxies spin, specifically looking at how fast stars at different distances from the center of a galaxy are moving. According to the laws of gravity and the distribution of visible matter, stars farther from the center should be moving slower, in the same way that the outer planets of our solar system move more slowly than the inner ones. But they were not moving slower. Stars far out at the edges of galaxies were moving just as fast as stars near the center. The rotation curves, as they are called, were flat when they should have been falling off. Something invisible was adding gravitational muscle. Something that was not showing up in any telescope. Vera Rubin's work was meticulous, careful, and ultimately impossible to dismiss. The case for dark matter had become very strong indeed. Part 3. Gravity is our best detector. Let us talk about gravity for a moment, because it is really the hero of this entire story. Gravity is the force of attraction between anything that has mass. Every single thing that has mass pulls on every other thing that has mass. You pull on the earth. The earth pulls on you. The moon pulls on the oceans. The sun holds the planets in their paths. And galaxies pull on other galaxies across distances so vast they are nearly impossible to imagine. The important thing about gravity is that it does not care whether something is visible or not. It does not care whether something is giving off light or absorbing light or doing anything at all with the electromagnetic spectrum. If something has mass, it has gravity. Period. This makes gravity an extraordinarily useful tool for detecting things that cannot otherwise be seen. It is like a universal handshake. You might not be able to see someone standing in a completely dark room, but if they are pulling on you, you know they are there. And that is precisely how astronomers study dark matter. They look at how gravity is behaving in various parts of the universe, and they ask whether the visible matter they can account for is sufficient to explain that gravitational behavior. Over and over again, in situation after situation, the answer has been no. There is too much gravitational pull for the visible matter to explain. Something extra is there. One of the most dramatic examples of this gravitational detective work involves something called gravitational lensing. When light travels through space and passes near a massive object, the gravity of that object bends the path of the light. This is a real, observed phenomenon predicted by Einstein's general theory of relativity and confirmed many times over. Think of it like this. Imagine holding a magnifying glass over a piece of text. The glass bends the light coming from the text, making it appear larger or distorted. A massive object in space does something similar to the light passing by it. Astronomers can measure exactly how much the light is being bent, and from that measurement, they can calculate how much mass is doing the bending. When they do this calculation in cluster after cluster of galaxies, the mass required to produce the observed lensing is far greater than the mass of all the visible stars, gas, and dust combined. The invisible scaffolding of dark matter reveals itself through its gravitational fingerprints, even when it refuses to show its face. Part 4. How much dark matter is there? Here's a number that might give you pause before sleep. According to the best current measurements from space telescopes and detailed surveys of the cosmic microwave background, which we will explain in a moment, ordinary matter, the kind made of atoms, accounts for only about 5% of the total energy and matter content of the universe. Only 5%. Dark matter accounts for approximately 27%. And the remaining 68% is something called dark energy, which is an entirely different mystery that we will not dive into tonight. For now, let us sit with that 5 and 27. That means the stars, the planets, the oceans, the mountains, the entire periodic table of elements, every galaxy you have ever seen in a photograph, every atom in your body. All of it together represents just 5% of what is out there. The overwhelming majority of the universe is something we cannot directly see or touch. Now, how do scientists arrive at these numbers with such apparent confidence? One major line of evidence comes from studying the cosmic microwave background, which is often abbreviated as CMB. The CMB is essentially the afterglow of the Big Bang. In the very early universe, everything was incredibly hot and dense, and the universe was filled with a glowing plasma of charged particles. As the universe cooled and expanded over hundreds of thousands of years, the plasma settled down into neutral atoms, and the light that had been trapped inside was released. That ancient light still exists today. It fills the entire sky in every direction, but it has been stretched out by the expansion of the universe into the microwave part of the spectrum, which means it is invisible to our eyes but detectable with specialized instruments. Telescopes like the Planck satellite have mapped this ancient light in extraordinary detail, measuring tiny variations in temperature across the sky. By studying the patterns in those temperature variations, cosmologists can infer the composition of the early universe. The precise ratios of ordinary matter, and dark energy are encoded in the structure of the CMB, the way the ingredients of a recipe are encoded in the flavor of a finished dish. Scientists have now read that recipe quite carefully, and the 27% figure for dark matter is one of the clearest things written there. Part 5. What dark matter is not. When people hear that most of the universe is made of invisible matter, a natural first instinct is to wonder whether it might just be ordinary matter that we have missed. Perhaps there are countless black holes out there. Perhaps clouds of cold gas are lurking in the darkness between galaxies. Perhaps enormous numbers of very dim, very faint stars are out there waiting to be discovered. These are all perfectly reasonable guesses, and scientists have checked each of them carefully. The general category of these hypotheses has a rather charming name. They are called MACHOs, which stands for Massive Astrophysical Compact Halo Objects. The idea is that dark matter might be made up of large, compact, ordinary objects that are simply too dim to see easily. Brown dwarfs, which are failed stars that never quite got hot enough to fuse hydrogen. neutron stars, which are the incredibly dense remnants of dead stars. Rogue planets drifting through space with no star to orbit. And yes, black holes. Scientists spent years looking for machos using a technique called microlensing. Remember gravitational lensing from our earlier discussion? When a massive object passes in front of a distant star, its gravity briefly bends and brightens the starlight. By watching millions of stars over long periods of time and looking for these brief brightenings, astronomers can detect objects that would otherwise be completely invisible. They found machos, but not nearly enough of them. The number of macho events was far too low to account for the total amount of dark matter required by the gravitational evidence. Machos exist, but they are a minor character in this story, not the main one. There is also a deeper problem with the macho hypothesis. Ordinary matter, whether it is in a star or a black hole or a cold gas cloud, is made of the same protons and neutrons and electrons that everything else is made of. And the abundance of those particles in the universe is constrained by the physics of the early universe, in particular by a process called Big Bang nucleosynthesis. The calculations of how many protons and neutrons could have been produced in the first few minutes after the Big Bang simply do not leave enough room for ordinary matter to account for dark matter. The math does not work out. Dark matter, whatever it is, appears to be made of something fundamentally different from the particles that make up you and everything you have ever touched. Part 6. Enter the particle physicists. At this point in our story, the astronomers had done their part. They had built an overwhelming case that something invisible was out there, that it was not ordinary matter, and that it was spread throughout the universe in enormous quantities. Now it was time for a different group of scientists to weigh in. The particle physicists arrived at the table. Particle physics is the study of the most fundamental building blocks of matter and energy. Over the 20th century, physicists built a remarkably successful framework called the Standard Model, which describes all of the known particles and forces in nature. It includes the quarks that make up protons and neutrons, the electrons that orbit atomic nuclei, the photons that carry light, the gluons that bind quarks together. The Higgs boson, famously confirmed at CERN in 2012. The Standard Model is a spectacular achievement, but it does not include dark matter. Whatever dark matter is, it sits outside the Standard Model. It is something new. Now, this is actually not as alarming as it might sound, because particle physicists had already been thinking for other reasons that the Standard Model was incomplete. There are theoretical puzzles within particle physics that many physicists believe require new particles to solve. And one of the most popular proposed families of new particles happen to have exactly the properties that dark matter would need to have. These are called WIMPs, weakly interacting massive particles. The name describes their two key characteristics. They are massive, meaning they have substantial mass and therefore substantial gravitational influence. And they are weakly interacting, meaning they only interact through gravity and through something called the weak nuclear force, which is one of the four fundamental forces of nature and is responsible for certain types of radioactive decay. Because WIMPs do not interact through electromagnetism, they do not emit, absorb, or reflect light. They are genuinely invisible in the electromagnetic sense. They pass through ordinary matter like ghosts. Trillions of them, by some estimates, may be passing through your body at this very moment, sailing through the Earth itself without the slightest disturbance. The WIMP hypothesis became enormously popular in the 1980s and 90s, and for good reason. It simultaneously solved a problem in cosmology and addressed puzzles in particle theory. That kind of dual explanatory power is extremely attractive to scientists. The search for WIMPs became one of the most intense projects in modern physics. Part 7. The Bullet Cluster, a Smoking Gun. Let us take a moment away from particle theory and return to the sky, because there is one piece of observational evidence for dark matter that is so clear and so striking that it deserves its own quiet moment of appreciation. In 2006, a team of astronomers studying a structure called the Bullet Cluster published results that many scientists regard as among the strongest direct evidence for dark matter ever observed. The Bullet Cluster is actually two galaxy clusters that collided with each other hundreds of millions of years ago. It is located about 3.8 billion light-years away from us, which means the light we are seeing left there before complex life existed on Earth. When two galaxy clusters collide, something very interesting happens to their different components. The stars within the galaxies behave like a sparse spray of particles. Because the individual stars are separated by such enormous distances relative to their own sizes, they largely pass through each other without colliding, like two swarms of bees passing through each other. The stars keep moving and largely maintain their original trajectories. The hot gas that fills the clusters is different. Gas is not sparse. It interacts with itself through electromagnetic forces. When the two clouds of gas collide, they slow down and pile up in the middle, like two streams of water meeting head-on. This hot gas emits X-rays, which astronomers can detect with space-based telescopes. Now here's the remarkable part. Using gravitational lensing, astronomers mapped where the mass of the two clusters actually was located after the collision. They found that the mass, most of it, was not in the middle where the gas had piled up. It was out ahead of the gas, with the stars. Something had passed right through the collision without slowing down. Something that interacted gravitationally but not electromagnetically. That something was dark matter. The collision had effectively separated the dark matter from the ordinary matter in a way that could be directly observed. The two clouds of dark matter had passed through each other the way the stars had, barely interacting, and they were now sitting on either side of the hot gas pile in the center. It was not a theoretical argument. It was not an inference from rotation curves or lensing statistics. It was, as close as science gets, a picture. A snapshot of dark matter behaving exactly as the theory predicted. Part 8. How scientists try to catch dark matter. Given how strongly the evidence points toward the existence of dark matter, the next logical question is whether we might ever actually detect a dark matter particle directly. This is an extraordinarily challenging project, but scientists are pursuing it with great ingenuity and enormous effort. There are three main strategies for detecting dark matter, and scientists often describe them as three different ways to look at the same interaction from different angles. The first strategy is called direct detection. The idea is to build an incredibly sensitive detector, place it deep underground to shield it from cosmic radiation and other interference, and then wait. If a dark matter particle happens to pass through your detector and nudges one of its atoms even slightly, that tiny collision would register as a signal. The challenge is that these collisions are expected to be extraordinarily rare, even if trillions of dark matter particles are passing through every second. The signal would be faint to the point of near impossibility. Experiments pursuing this strategy include names like LUX, which stood for Large Underground Xenon Experiment, and its successor LZ, as well as Xenon and Panda X. These experiments use tanks of very pure liquid xenon or similar substances, chilled to extremely cold temperatures, surrounded by layers of shielding. They have been running for years, growing ever more sensitive, and so far they have not found a confirmed dark matter signal. But each generation of the experiment pushes the sensitivity further, narrowing down the space of possibilities. The second strategy is called indirect detection. Instead of waiting for a dark matter particle to bump into a detector, this approach looks for the products that might result when two dark matter particles meet each other and annihilate, converting their mass into energy and ordinary particles. If dark matter particles are drifting through the universe and occasionally collide with one another, those collisions might produce gamma rays or other particles that telescopes could detect. The Fermi Gamma Ray Space Telescope has been scanning the sky for exactly this kind of signal, particularly from the center of our galaxy and from dwarf galaxies, where dark matter is expected to be especially dense. Some intriguing hints have appeared over the years, but nothing that has risen to the level of a confirmed detection. The third strategy is production at particle accelerators, most famously at CERN's Large Hadron Collider. The idea is to smash particles together at such extreme energies that dark matter particles might be produced from the collision, briefly flickering into existence before escaping the detector unobserved. Scientists would detect their presence by noticing a missing piece, energy that should have been there based on the collision but appears to have disappeared. This signature is called missing transverse energy, and physicists have been looking for it carefully. Part 9: Axions, Sterile Neutrinos, and Other Candidates. WIMPs have received an enormous amount of attention, but they are not the only dark matter candidates on the table. As the most sensitive WIMP detectors have come up empty year after year, physicists have been giving more serious thought to other possibilities. One very popular alternative is the axion. Axions were actually proposed in the late 1970s for a completely different reason. Physicists were trying to solve a puzzle within the standard model called the strong CP problem, which involves a subtle asymmetry in the way the strong nuclear force should behave compared to how it actually behaves. A theorist named Helen Quinn and a physicist named Roberto Pecchiai proposed a solution that required the existence of a new, very light particle. Frank Wilczek and Steven Weinberg independently noticed that this proposed particle would be produced in large numbers in the early universe and would behave very much like dark matter. Axions, if they exist, would be vastly lighter than WIMPs. They would also be extremely numerous. They would interact with ordinary matter through a very faint coupling to photons, which gives experimenters a potential handle on detecting them. Under the right conditions, an axion moving through a strong magnetic field might spontaneously convert into a detectable photon. Experiments like the Axion Dark Matter Experiment, or ADMX, are designed to exploit exactly this possibility. They use powerful superconducting magnets and microwave cavities to create conditions where axion-photon conversion might occur at a detectable rate. It is a delicate, patient business. Another candidate is the sterile neutrino. Ordinary neutrinos are already quite ghostly particles. They have very tiny masses and interact only through the weak force and gravity, which means they zip through ordinary matter with almost no interaction. Trillions of solar neutrinos pass through your body every second without you noticing. Sterile neutrinos are an even more detached cousin. They are hypothetical particles that interact only through gravity, not even through the weak force. They would be almost completely invisible to detection. Some theorists have proposed that sterile neutrinos produced in the early universe could account for at least a portion of dark matter. There are also more exotic proposals. Primordial black holes, formed in the very early universe before any stars existed, have attracted renewed interest in recent years. Ultralight dark matter, sometimes called fuzzy dark matter because of the way its quantum nature would create fuzzy, wave-like structures on very small scales, is another intriguing possibility. The field is genuinely open and genuinely exciting. Part 10: Dark Matter and the Shape of the Universe. One of the most beautiful things about dark matter, despite all the mystery surrounding it, is that its gravitational influence has left visible fingerprints on the large-scale structure of the universe. The universe is not a uniform sea of galaxies spread evenly in all directions. It has a magnificent architecture. Galaxies cluster together along vast filaments, like droplets of dew along a spider's web, and between these filaments lie enormous voids, regions nearly empty of galaxies that can stretch hundreds of millions of light years across. This structure is called the cosmic web, and its existence is deeply connected to dark matter. In the very early universe, just after the Big Bang, the distribution of matter was almost, but not quite, perfectly uniform. There were tiny fluctuations, regions that were very slightly denser than average and regions that were very slightly less dense. Over time, gravity amplified these tiny differences. The denser regions pulled in more matter. The less dense regions lost matter to their denser neighbors. Over hundreds of millions of years, the dense regions grew into the filaments and clusters we see today, and the voids grew emptier. The rate at which this structure formed, and the detailed pattern it took, depended crucially on the amount and character of dark matter. Ordinary matter alone would not have been able to form structures as quickly as we observe. The deep gravitational wells carved out by dark matter in the early universe served as seeds around which ordinary matter could gather. The gas and dust that would eventually form stars and galaxies fell into the gravitational pockets that dark matter had already prepared. Think of dark matter as the scaffolding that was erected first, before the visible universe was built. Like the steel framework inside a building that stands invisible once the walls and floors are in place. You cannot see the scaffolding once construction is complete, but without it, the building could not have taken shape. Cosmological simulations, which are enormous computer models of the universe's evolution, confirm this picture beautifully. When you include dark matter with the right properties in the simulation, the universe that results looks remarkably like the universe we actually observe, with its filaments, its clusters, its voids, its galaxies. When you leave dark matter out of the simulation, the result looks nothing like our universe. The match between theory and observation is one of the strongest arguments for dark matter's reality. Part 11: The Challenge of Alternative Explanations. Science proceeds by considering all reasonable alternatives, and it would be unfair not to mention that some scientists have proposed explanations for the dark matter observations that do not require any new particles at all. The most prominent of these alternatives is called modified Newtonian dynamics, often referred to as MOND. It was proposed in the 1980s by an Israeli physicist named Mordechai Milgram. The core idea of MOND is that our understanding of gravity might be slightly wrong at very low accelerations. Rather than proposing a new kind of matter, MOND proposes a modification to the law of gravity itself. In regions where gravitational acceleration is extremely weak, gravity might behave differently than Newton's equations predict. When applied to the rotation curves of galaxies, MOND works remarkably well. It can reproduce the flat rotation curves that originally motivated dark matter in the first place, without requiring any invisible matter at all. For For this reason, it attracted a devoted following and has been developed and extended by various researchers over the decades. However, MOND struggles considerably with other lines of evidence. The bullet cluster is particularly difficult for it to explain because the separation of visible matter from the gravitational mass is so clear and so dramatic. A modification to gravity alone cannot easily account for a situation where the mass appears to be in a different location than the visible matter. MOND also has difficulty explaining the cosmic microwave background patterns, the detailed structure of galaxy clusters, and the large-scale structure of the universe. Various extensions and relativistic versions of MOND have been proposed to address some of these problems, but none has fully succeeded in matching all the observations simultaneously. The consensus view among cosmologists today is that the full body of evidence favors the existence of actual dark matter particles rather than a modification to gravity. However, it is worth noting that this consensus has been earned through careful, ongoing comparison of theory and observation, and that healthy skepticism about any hypothesis, including dark matter, is part of how science works. Milgram's original insight that galaxies behave in a surprisingly regular way at low accelerations remains an important observation that any complete theory of dark matter may eventually need to address. Part 12: Dark Matter in Our Own Galactic Backyard. Our own galaxy, the Milky Way, is embedded in a vast cloud of dark matter called a dark matter halo. This halo extends far beyond the visible edge of the galaxy, reaching out into intergalactic space. It is roughly spherical in shape, much more so than the flattened disk of stars and gas that forms the visible part of the galaxy. The presence of this dark matter halo was inferred from exactly the same kind of rotation curve analysis that Vera Rubin applied to other galaxies. The stars and gas at the outer edges of the Milky Way are moving faster than the visible mass alone could account for. Something invisible is providing extra gravitational pull, holding the outer galaxy together and keeping its stars in their orbits. Estimates of the total mass of the Milky Way's dark matter halo vary, but it likely amounts to several times the mass of all the visible matter in the galaxy combined. Our entire galaxy, the hundreds of billions of stars, the gas, the dust, the central black hole known simply as the supermassive black hole at our galactic center, all of it is embedded in and gravitationally dominated by this invisible shell of dark matter. The density of dark matter in our local neighborhood, meaning the region of the galaxy near our solar system, is estimated to be roughly 0.3 giga-electron volts per cubic centimeter. That sounds like a very precise and somewhat arcane number, and it is, but it is important because it represents the local dark matter environment that any Earth-based detector would be operating in. There is dark matter passing through this room right now, and this number is our best estimate of how much. Our solar system orbits the center of the Milky Way at a speed of roughly 220 kilometers per second, and as we move through the galaxy, we are moving through this cloud of dark matter. The dark matter particles, if they are WIMPs or axions or something similar, are streaming past us and through us constantly. The detectors deep underground are watching for the rare moments when one of them leaves a trace. There are also some intriguing observations of our galactic center that have suggested a possible signal. The center of the Milky Way is an extremely dense region, and dark matter density is expected to peak there. Some analyses of gamma-ray data from that region have shown a slight excess of gamma rays, possibly consistent with dark matter annihilation. The interpretation of these observations is still being debated among scientists. Part 13: What happens if we never find it? This is a question that sits quietly at the edge of every dark matter discussion. What if the detectors keep running and keep finding nothing? What if the particle colliders produce no dark matter particles? What if decades of searching yield only upper limits on cross-sections and masses? What do we do with the gravitational evidence then? It is a question worth sitting with honestly. The history of science contains many episodes where a phenomenon was clearly real, but the explanation for it took a very long time to find. The nature of light was debated for centuries before Maxwell's equations and later quantum mechanics gave us the full picture. The cause of infectious disease was unknown for most of human history, even as the diseases themselves were vividly real. Plate tectonics was not accepted as a scientific consensus until the middle of the 20th century, even though the continent's shapes had been suggesting something like it since maps were first drawn. Dark matter's gravitational effects are so thoroughly documented, so consistently observed across such an enormous range of scales and contexts, that the existence of something causing those effects is not seriously in doubt. What remains in doubt is the identity of that something. If WIMP searches keep coming up empty, the field will continue shifting attention toward other candidates. Axions and axion-like particles would receive more resources. Primordial black holes would be studied more carefully. New theoretical proposals would emerge. The community would adapt. It is also possible that dark matter particles interact so weakly with ordinary matter that the required detectors are simply beyond our current engineering capabilities. In that case, the evidence may continue to accumulate on the astrophysical side through ever more detailed mapping of dark matter's gravitational influence using lensing surveys, galaxy dynamics, and the CMB, even as direct particle detection remains out of reach. None of this changes the reality of the phenomenon. The stars at the edges of galaxies are still moving faster than they should. The bullet cluster's mass is still displaced from its gas. The large-scale structure of the universe still matches the predictions of models that include dark matter. The evidence is not going anywhere, even if the particle itself remains shy. There is something almost poetic about that. The universe holds its secrets carefully. Part 14: The Frontiers of Dark Matter Research. As we near the end of our journey tonight, let us take a brief look at where the science is heading. Dark matter research is an active and rapidly evolving field, and there are several exciting developments on the horizon. On the observational side, a new generation of sky surveys is transforming our ability to map the distribution of dark matter across the universe. The Vera Rubin Observatory, named in honor of the astronomer whose rotation curve work was so pivotal, began its legacy survey of space and time recently. Over the course of a decade, it will photograph the entire accessible sky repeatedly, accumulating an unprecedented record of the positions and shapes of billions of galaxies. From those shapes, scientists can measure weak gravitational lensing, the tiny, statistical distortions in galaxy shapes caused by dark matter along the line of sight, with extraordinary precision. The Euclid Space Telescope, launched by the European Space Agency, is conducting a similar survey from orbit, mapping the large-scale structure of the universe over the past 10 billion years or so of cosmic history. Together, these surveys will produce the most detailed maps of dark matter ever made, tracing the cosmic web across enormous spans of time and space. On the particle detection front, the next generation of underground detectors is being designed and built. LZ, the LUX Zeppelin experiment in South Dakota, is currently operating with sensitivity many times greater than any previous WIMP detector. Its results over the coming years will either find something or push the boundaries of what kinds of WIMPs can exist into increasingly tight corners. For Axions, the ADMX experiment is being upgraded and new experiments with different frequency ranges are coming online. The space of possible axion masses is vast, and searching it systematically requires many different experimental approaches. There is also growing interest in using astrophysical observations to constrain dark matter's properties in ways that complement laboratory searches. The shapes of galaxies and galaxy clusters, the structure of small dwarf galaxies orbiting the Milky Way, the patterns of star formation in the early universe, all of these carry information about how dark matter behaves on small scales. Some observations have suggested that dark matter might interact with itself in subtle ways, creating what physicists call self-interacting dark matter. These hints are being pursued carefully. The coming decade is expected to be transformative for the field. Whether it brings discovery or deeper constraints, the science will move forward. Part 15, Reflections. We have covered a great deal of ground tonight, and I want to take a few gentle moments to bring it all back together before we close. We began with the simplest idea, that matter is stuff made of atoms, and atoms interact with light, which is why we can see things. We then discovered that the universe appears to contain an enormous amount of matter that does not interact with light at all. This invisible material was first proposed by Fritz Zwicky in the 1930s, who noticed galaxy clusters behaving as if they were heavier than they looked. It was confirmed most powerfully by Vera Rubin in the 1970s, who showed that galaxies spin in a way that only makes sense if they are wrapped in vast, invisible halos of additional mass. We saw how gravity is the key tool for studying dark matter. Because everything with mass has gravity, and because dark matter has mass, its gravitational influence leaves clear, measurable signatures across the universe. The bullet cluster gave us a near-direct view of dark matter behaving differently from ordinary matter during a galactic collision. We explored the numbers. Ordinary matter makes up only about 5% of the universe's total matter and energy. Dark matter makes up about 27%. These figures come from multiple independent lines of evidence, most convincingly from the patterns in the cosmic microwave background, the ancient light left over from the Big Bang. We considered what dark matter might be made of. WIMPs have long been the leading candidate, but they have not yet been detected despite extensive searches. Axions, sterile neutrinos, primordial black holes, and other possibilities remain open. We also considered the main alternative explanation, modified Newtonian dynamics, and saw why the full body of evidence makes most cosmologists more confident in actual dark matter particles than in a modified gravity law. And we looked ahead to new surveys and new experiments that will push the search forward in the coming years. The universe is, as ever, patient. It has been holding this secret for billions of years. We have only been asking the question seriously for about a century. In the long view of things, the search has only just begun. And on that note, thank you so much for spending this time with me and with the cosmos. Whether you found your sleep tonight, or your focus, or simply a few quiet moments of wonder, I am genuinely glad you were here. This is the Nocturnal Astronomer, and I'll see you next time.